Hello everyone, we are delighted to present to you our project titled Mapping the Academic Landscape. Our team comprises of Aditya Chawla, Saurabh Mishra, Apurv Anand, and Paras Meher. Our project aims to create a knowledge base of research areas of professors at IIT Kharagpur and fetch the results using OWL query. The goal is to simplify the process of finding the right guide for research work for students at IIT Kharagpur and enhance the academic community by fostering collaborations and encouraging the exchange of ideas between researchers at the institute. To achieve this goal, our team used data scraping, preprocessing, and clustering techniques to gather and organize the data. We then generated a CSV file and an ontology with Protégé for further analysis and visualization. The motivation for this project is to create a platform that will make it easier for students at IIT Kharagpur to find professors who are working in their area of interest. By providing a single platform that aggregates information about the research areas, H-index, and citations of professors at IIT Kharagpur, we aim to simplify the process of finding the right guide for research work. This project will benefit students at IIT Kharagpur who are looking for a mentor or guide for their research work, as well as professors at the institute who are seeking to collaborate with other researchers or find potential students to guide in their research works. Overall, our project has the potential to significantly benefit the academic community at IIT Kharagpur by creating a comprehensive and accessible resource for researchers and students alike. The first part of our project included data scraping. As part of our project, we collected data from the official website of IIT Kharagpur for each department, which included the names and research areas of the faculty members. To extract the necessary information from the HTML content of the web pages, we employed the request and beautiful submodules, which are commonly used in web scraping applications. By utilizing these techniques, we were able to efficiently gather and process the relevant data required for our project's objectives.
Hello, this is Paurus. So, after data scrapping, we obtained that there are 390 unique professors and 1545 research topics. So, owing to huge number of research topics, we decided to cluster related topics into a broader research area. So, basically, for example, computer vision, natural language processing, machine learning, all these research topics will fall into a similar domain name as artificial intelligence and machine learning. So, like we have decided to cluster all these similar research topics. So for this we are using three models: LDA, BERT with k-means, and BERT topic with hierarchical DB scan clustering. We have used these three topics for clustering. So before clustering, like we are doing the pre-processing on the data. The like these are the remove the punctuation, then lowercasing all the characters, removing the stop words, then making the bigrams and the trigrams to capture the words that like occur more frequently, then the lemmatization. Now the first model we are using is the LDA. So basically this is a generative probabilistic model, and like in this model we are looping for the number of topics and like calculating the coherence score. Coherence score basically indicates like how well the topics capture the underlying themes in the corpus. The more is the coherence score, more is the better is the performance of the model. So on x-axis we have plotted the number of topics, and y-axis is the coherence score. We found that it is maximum at 35, so we choose the optimum number of clusters to be 35. So using these 35 as the number of cluster, we train this LDA model, and these are the results. This is I'm plotting the clusters on the 2D plot here, and like in the cluster 2 we can see these are the frequently occurring words, but the results are not good. As we can see, there are like structure, rheology. These words do not like are like slightly not related to the topic. So the problem with this model was lack of context from the outside the data, and also the data was not good. So we moved to another model, but with k-means clustering. Here we got the embeddings from the research topic and for the research topic, and from using the BERT model, and we use k-means clustering. But again, the results were not much satisfactory again with this model, because like it was also using the outliers for clustering, and like it was reducing the quality of the clusters. So then we move with another model, which is the BERT topic with hierarchical DB scan clustering, and like it was giving the best result. So here is the architecture of the model. It has basically three steps: embedding the textual data, clustering the documents, and creating a topic representation. Then after fitting this model, so after training this model, these are the results. So once the model is trained, like we have trained it for the 35 clusters, because these 35 we have obtained from this our LDA model. So here we can see that um, for so topic 0, so it has these topic 0 is the topic which has like these set of words occurring frequently in it. Topic similar for topic 1, 2, 3, and I'm printing the top 8 topics and the frequently occurring words in that topic. So we can say that the clusters are formed pretty well. See, like topic 0 is related to machine learning, 1 is related to fluid. Similarly, 2 is related to powers and solar energy. And like here I am plotting on 2D axis using PCA. I am plotting like how what is the distance between the clusters and how like what is their location on the 2D plane. Like on the more dimension plane, there won't be much overlap. And one more the problem using this model was there were of too many of outliers in our outlier research research areas in the model. So here we can see the topic -1, the counter 250 means there were like 250 outliers which are like not properly classified. So using this bird topic model, because they are like slightly unrelated to the other topics. So look, this was the problem. And like what we did is basically for these topics we again fitted the model, and like the output will give us the vector of the probability, like with what is the probability that this outlier will fall into one of these topics. And like what we are selecting the putting that the topic into that cluster for which the probability is maximum. So once is done, like these are the final results we have got. So these are the broadly like these are the sum of the topics, and these are the count of the research areas, like the sub research areas in this topic. So like the names, like we have manually given the names to this, and like these are the count. So we can see artificial intelligence, machine learning, then advanced battery management systems for electrical vehicles. These are all the results. And the final results like here I am showing how are the clusters formed. So let's say the the cluster name is artificial intelligence and machine learning, and these are the subtopics included in it. So machine design, AI for cognitive science, artificial intelligence, NLP. So these are some of the sub research areas in this broader research topic. Similarly, see computational fluid dynamics, and these are all the research areas, advanced battery management systems for electrical vehicles, and all the sub research topics in these broader research topic. So basically, and then like for all the 35 topics we have got this list. And like I am storing it in the form of dictionary, with the dictionary key to be the name of this research topic, and the value of this will contain a list of all the research topic which are subtopic of sub which follows into the subdomain of this um, broader research topic. So now my friend Saurav will continue from this. Thank you.
Once we get the dictionaries, we use the relevant information to generate the CSV file. For this, we make use of pandas library, and the generated CSV file has 3 columns: name of the professor, department, and broad research area. But something is missing here. In addition to this, we also want to include the information about H-index and citation of the professors. Hence, our next task is to acquire them. For that, we use Google Scholar and fill the H-index and citations manually for the 390 professors. After doing this, our final CSV file look like this, with addition of 2 more columns: H-index and citation. Next, we proceed to design the ontology. We declare 3 classes: department to include all the departments, professor class to include all the professors, and research class to include all the 35 research areas. We also declare 4 object properties: has department with its inverse is department of, and has research area with its inverse is research area of. To add the H-index and citation information, We also include the has h index and has citation data property with data type being XSD integer. Now, once we declare all the classes and properties, our ontology looks like this. Now, our next step is to add the axioms. For this very purpose, we make use of the generated CSV file. To import the axioms from the CSV file, we make use of self-i plugin in the Protégé. The window of the self-i looks like this. We open our CSV file in Excel format here, and as we can see, all of the cells are displayed here. After this, we select all the rows except the first one. Then we apply transformation rules. As shown here, we iterate over column A and declare all the entities in that column as professor. We also state property value to be coming from B, followed by uh, we also state the facts associated with each entity in the column A, and we declare had department property value to be coming from B, followed by has research area coming from column C, with H index coming from D, and lastly has citation coming from the column E. After this, we add the generated axioms to the ontology. Now our ontology is complete and ready for use. In the next section, Apur will show the demo of the created ontology. Thank you.
So hello, I am Apurv, and let's have a demo for this ontology that we have designed. So this is the ontology, and as we can see, these are the entities, the classes, the department class to have all the department instances, the professor class to have all the professors, and the research area to have all the research area instances. We have the object properties of has department, has research area, and their inverses, that is department of and is research area of. We also have the data properties of has h index and has citation. We have these individuals, that is where we store information about the professors, the department, or any of the research areas. Let's see for like Professor Abhijit, who has research area machine learning, algorithmic design, and cybersecurity and information protection, has department CS, has H index 13, and has 800 citations. So let's move on to have a query for any professor who has research area of big data analytics. So let's do that. Has research area big data analytics and information retrieval in various domains. Let's execute this query to find out the professors. So we have got 18 professors. Let's filter out the data to have only the professors whose department is either CS or AI. This department AI, or has department CS. So let's execute this query. So now we have got 11 professors. If we want to further filter out, then we can also filter out on the basis of H index or number of citations. Let's filter on the basis of H index. So let's do that. Has H index some integer which is greater than 10, so that we have professors whose H index is greater than 10. Let's execute this query to find 9 professors. So in this manner, any student can find his or her interested research area and the professors who are working on that, and can further filter out if they want on the basis of department or H index or the number of citations. Further future work can be done on this tool to integrate it with natural language. So overall, this was our project. So thank you.